ready to talk about planes? Let's do it. All right, the motivating question. Thank you. The motivating question for today is, what information would you need to know to define the equation of a plane? And I asked that question in the same spirit as you might have thought about the question like, how do we nail down a line? Well, remember, 2 points will do, right? 2 points defines a line. Or point and slope, or slope and a point, or length of the normal and the angle of the normal. There are a couple different sets of things you could give me, but certainly 2 points would do. 3 points defines a parabola. Did you know that? 3 points defines a parabola. Right? 5 points defines a conic section. Any conic section. What else can we say? Or what about a plane? What would you like to say? What information could you convey that would be like necessary and sufficient to communicate to someone else so they know exactly which plane in space that you're talking about? And by a plane, of course, maybe we should stop and say we just mean a flat surface, all in space, somewhere floating in space. How do we nail it down? Maybe there's a very quick answer that I think everyone goes with. So what's that? 2 points. Well, that doesn't quite nail down the plane.
Maybe you have 2 points on the line and then use a long line.
Will 3 points do?
For a plane?
I think the proof is in watching it up here, right? I mean, that certainly defines one plane. There's not another plane that could go through those 3 points, just that one. Right? Yeah, we do have to be very careful. What do we need to say? 3, what kind of points? Non-collinear points, because then otherwise you're still back to the wobble, right? 3 non-collinear points will do. Anyone have another creative way of defining a plane? Give me other ways of doing it. A line and a point not on the line, I guess we should say again. Right, that certainly works. Yeah? What else?
A big square.
A big square?
Really big.
Okay, like the plane itself? Like, okay. Yeah, Francis?
Any 2 non-overlapping lines?
Well, then you need to...
Or not like directly on top of it.
Okay, but what do? You do need to require maybe that they... You can't just have 2 lines like this.
Non-parallel.
These lines are not parallel. That doesn't define a plane though. Yeah, 2 intersecting lines. Like the ones from the warm-up, wouldn't that work? If they're intersecting, then you could define a plane that contains them both. And they can't be the same one in the same line, that's true. Anything else? Okay, I mean that's fine. I don't have an answer key here or something. I just was wondering what you come up with. I will say, you'll be surprised, none of those things are what we're going to use today. We're going to use, well, I should say, we do the 3 point, we will do all those things eventually, but we're going to use the following 2 things. We're going to use a point and a normal vector to the plane. So just verify with me from a physical standpoint that this does seem to make sense. If I have 1 point, so first of all, that nails down the plane partially. It has the plane going through this 1 point and wobbling quite a bit. But then the other thing we'll supply is a normal vector to the plane, which is an idea that's a little strange maybe. But it kind of says, okay, hey, you're wobbling. Could you just fix yourself and point in that direction, say? And then the plane is like, okay, yes, boom. And now we're locked into position. Do you see? Like it's going to go through this point, and then as soon as you specify, face yourself in that direction, it obeys. Okay, so if we have those 2 things, can you see how maybe that will define a plane? I know that might seem weird, and we will do the other things too. I think we have 3 points we'll do today. Define a plane. We'll do that one as well. But it all is going to be based off of this analysis. We'll also, I think I have a warm-up where I have 2 lines somewhere along the lines. I have that too. Yeah.
So this is kind of like the one where we said that we define a line and a point that's not on the line.
Not quite, because it's not going to be a point and a line. It's going to be a point and a normal vector of the plane. I think you're thinking of a line that like lives in the plane. I'm not thinking about that. I'm thinking about a vector here that points out of the plane, right? that's perpendicular to every vector that you could build in the plane. You build some vectors in the plane, no matter which vector you build that lies in the plane, it will be perpendicular to this normal vector. So this is what's being given. It's a normal vector and a point. Yeah, go ahead.
Does normal and orthogonal mean the same thing?
Sure, yeah.
All right.
Sorry, we keep using all these different words for the same thing. All right, so what must be true about a generic point if it's going to be in the plane? Well, first of all, here's what I'd like to do with this generic point. I'd like to build a vector from the point that was given. Keep in mind that these 6 letters, A, B, C, D, E, F, are all letters that are given to you, handed to you, say, in the problem. So D, E, F is a point in the plane, and X, Y, Z is a generic point that we purport to be in the plane. And what I'd like to start, just go with me on this, I'd like to build a vector from the point given to a generic point X, Y, Z. So what is the vector from D, E, F to X, Y, Z? What are its components? Yeah, X, keep going. Right. So this is a vector, do you agree? If X, Y, Z really is a point in the plane, then this vector lies in the plane, or lies in the direction of the plane. Do you agree? Because it goes from D, E, F to supposedly X, Y, Z, which is in the plane. So it points in the direction of the plane. You see what move we're going to make next with the blue direction, the normal vector now? What do we require be true about the blue vector and its relationship with the red vector? It should be orthogonal. And what demand does that have? Yeah, we need to set the dot product of the blue and the red to be 0, right? Don't we demand that if this is really a vector in the plane, then it must be orthogonal with the vector that has as its definition that it's the vector orthogonal to all vectors in the plane, right? And really, in some sense, we're kind of done. I mean, this will supply us with the equation of, now we'll work it out here. Actually, let's compute the dot product. I'm going to move all the constants here over to the other side. Things that don't involve an x or a y or a z. Yeah.
I was just wondering, is there anything like interesting about two vectors that have a cross product of 0? Because like I know if there's like a dot product of 0, there's something. Is there anything like the vector that you get when you get the cross product is like 0, 0?
Yeah. When do you get a cross product of 0? What 2 vectors do you have to cross in order to get a cross product of 0?
Parallel?
Yeah, if they're in the same direction. And that has a nice physical meaning too, because if they're in the same direction, is there a vector, a unique vector that's perpendicular to those 2 vectors simultaneously? And the answer is no. There's like a whole set of vectors, right? There's like an infinite. You only get a unique cross product when you have 2 vectors that aren't in the same direction, right? Then we can definitely talk about the vector that's orthogonal to both. There's more we could say about that, but yeah, it's possible to get a cross product of 0. All right, so notice that this is all a constant over here. All of that, AD plus BE plus CF. So I'm going to just condense that, and I want to make sure you're clear. If you ever see an equation of the form something times x plus something times y plus something times z equals something, some number, then that's a plane. That's the equation of a plane. I'll put it in a box here. Keep in mind that here we have capital A, capital B, and capital C. Those are the same as little a, little b, little c. So there's no major fast one we pulled on you there. But we have pulled a little bit of a fast one on this. I'm just going to replace all of these letters with capital D. Is that okay? Just keeping in mind that it's going to be a constant of some kind. But that doesn't correspond to lowercase d there. I hope you're okay with that. But that's a plane. The point is something times x plus something times y plus something times z equals something is a plane. And we should, before we leave this too, we should notice a couple very important things, right? A, B, and C, which are corresponding to little a, little b, and little c. That's just the what. If someone hands you the equation of the plane, you should be able to see right away the coefficients of x, y, and z are actually what? Aren't those the normal? There's not, like you're looking, if someone hands you the equation of the plane, you have immediate access to what the normal vector is. Right there, boom, done. What is D? That's a little strange too. What is that? What is AD plus BE plus CF? That, yeah, it's the dot product of the normal vector and the position vector to this point DE at. So it turns out that that's the case. But I actually don't mind us thinking through this every time we do one of these problems too. Blue times red, or dotted with red equals 0. That is a great way to get the equation every time. I'll put it in a box on this page too. There you go. Let's see if this applet link works. Let's see. So I should have maybe fired this up the moment I said we're going to use a point and a normal vector, just so you could be like have some buy-in. But you can imagine here. So we have some point. You get to say where it is. We have some normal vector. You get to say which way it points. Do you see how those two things together define a plane? Right? This idea that you can kind of say where the point's going to be. Come on now. And you can say where the plane's going to point, and that uniquely defines the plane, right? This is the picture that goes along with what we've been saying, right? All right. Yeah.
So, on the last slide, it said that the vector A, B, C is normal to the plane.
Yeah.
So can't we just take the A, B, and C from the beginning and just make them a vector?
Yeah. This is easy, is the point of that, right?
Oh.
It should only take you a second. If I give you a point in the plane and a normal vector, I expect this all to be done within 30 seconds. There you go. Oh my, wait, go, wait now. You're only at like 12 seconds right now.
You picked me?
I did.
You did?
It was not by purpose. On purpose.
Oh no. Do the other quarters of the second? Wait, is it just one thing?
Whenever Itai's ready, he's going to share with us.
Oh god.
Is it any new table mate? Oh.
He said, I expect it to be done in 30 seconds, but a minute and a half.
I might have been exaggerating.
Wait a minute, I just realized. How did you pick me? This is my luck.
You wanna volunteer on another behavior?
Yeah, sure.
Sam, you wanna bail Itai out here?
He knows what he's doing. You
Does
got
he?
this.
No, I don't.
I literally
No, he just asked to be bailed out. He said, all right, how do we do this?
Wait, he knows how to do it.
I don't.
3 points of the vector are A, B, and C. So we already know it's x minus 2y plus 4g.
Are you listening, Itai? Okay. And others too. You're not alone, and we love you no matter what. It is Valentine's Day. All right, Sam, keep going.
And then find the direction vector. So then you take 1 minus 1, 5 minus -2, -2 minus 4. Okay. Or plug it in.
Yeah, it's certainly true that we can. Yeah, I mean, certainly the way we could start this too is by actually doing what we did before: x minus 1, y minus z plus. and work this out here, and you'll get the right answer, right? How do we get this? What does that come out to be over here? -1 plus 10 plus 8 is 17. Yeah, or someone say it another way too. How did you get -17? What is that? Yeah, it's just that it ends up being just the dot product of these two things, but alright, we got it.
Maybe I can do it.
Hey, you're the one who said that.
Aiden, let's be charitable.
Okay, time for the best.
Yeah, you're smart.
How do you know?
Yeah.
About the cross product.
I did get the
Alright, I just thought I'd show you this particular plane we've been working with. Here's the 0.15 -2, and here's the normal vector, whatever it was. Okay?
I actually kind of get it.
And we'd like to show you the plane now, which is generated from this, okay? Does the plane contain the point? Is the plane pointing in the direction of the normal vector? Is that the normal vector to the plane? Yeah. Anyway, good times. All right, well now here comes the thing that you asked about earlier, right? Some of you, this is the first thing everyone went for. So we do want to come to this as well, you guys. We definitely want to be able to do this too. It's definitely something that should be able to be done. We're sure of it. But how do we come up with the equation of the plane that contains 3 points? Okay, well let me tell you, our to-do list is we'd like a point and a normal vector, wouldn't we? If we had those, we would just do what we just did, which is ends up being pretty simple. Well, we have plenty of points. Check. We use any one of those. And we just need a normal vector, really, is the big task. How do you get a normal vector to this plane is the big question here. What do you think, Ray?
Aaron, do you like take, like, let's say the last one, that's your point, and then the first two, you make the vector, and you make one that's orthogonal.
Oh, interesting. You're learning from our warm-up today, maybe, too. Right? Yeah, if we want to get out of the plane perpendicularly here, we need to find maybe some vectors in the plane and then form their what? Cross product, right? So let's get a vector orthogonal to the plane by doing that, okay? So which vectors would you like to make? I don't know why this doesn't have a name. Let's call it S. So we need to make, it doesn't matter, maybe we make QR, and so form that vector, and maybe QS or something. But any vectors in the plane will do. If you want to use someone out there, you can make like RS and SQ or something, whatever. You can do whatever. And then take their cross product. In fact, I'd be interested to see whether we should get the same answer at the end of this problem, regardless of what vectors you form, regardless of which order you cross them in, and regardless of which of the 3 points you use when you form the plane. So, but I'll do these if you want to follow along with the two I'm using. So -7 by -1. -3 minus 2 is -5. All right, so we'll cross those then, right?
Yeah.
And you can do QR cross QS, or you can do QS cross QR. It doesn't matter. You'll get the same. You won't get the same answer. You'll get, in either case, a vector that's orthogonal to the other two, though. Let's see if we can do this in our head then here too. This last part. -20. Check me on each one of these. You get -23i. And then remember, it's minus whatever's in the middle, J. Check me on all these. I guess -9. Let me just double check all those.
is when?
Wait, why would it'd be plus 34.
Remember that in the middle it's always minus that though, right?
Wouldn't it be minus
Well, I think that you actually get a positive 34 when you do these minus these. But then it's always the determinant of this first matrix times I minus the determinant of the second matrix times j plus the determinant of the third matrix times k. So it's always the opposite of whatever it comes up with in the middle. So you think you get their positive 34, don't you, for that one?
Yeah.
So it'll be minus 34.
Wait, no. Isn't it 7 times negative 5?
You wanna-
Isn't it 7 times negative 5 minus 1?
Negative 7 times negative 5
Yeah.
is positive 35. And then minus
Wow.
positive 1 is positive
I
34.
cannot believe I did that.
All right, so we're very close now. Which point would you like to use? We've got a normal vector now. Which point would you like to use? Whichever one you like. How about 302? Because there's a 0 in it, and that makes me happy. I like multiplying by 0. Whatever, but you actually, maybe someone else use a different one just to prove the point. It works. So what do we have? Negative 23x minus 34y minus 9z equals something. I don't know what. I'll dot that with 302 now. Oh, this is messy. Negative 68, 9, negative 69,
Negative 69
and negative 18.
It's negative 88.
Negative 88,
Yes, sir.
20, 69, 69 and 18. And if you want to multiply through by negative 1, you might want to do that, right? Just to make it look a little prettier. I think I have that. I think I have that instinct too, to want to make it look that way. I think. Guys, we did it.
Why did you do that? I don't make it positive.
Just for fun.
Oh.
Yeah.
What determines which two combinations we have to use? Like, why can't we
Doesn't matter.
use SR?
You should use SR and tell me how it goes.
Oh.
It should work. It should work.
It should work as
Yeah.
well.
That's what I said. You should be able to form any two vectors you like here. You should be able to form the cross product in either way. And then at the end, you should be able to use any point you like. And in all cases, you should get this lot, this plane.
Yes. You should.
Yeah, yeah.
I have two questions.
Yeah.
After the negative 23x, why did it become positive?
Just wanted
So you can factor out the negative 23. Is that
I just divided everything in the equation by negative 1.
And also, where did you get the negative 87? The 87 from?
This, I formed the dot product of this with one of these. I used 302, but it should be the same. You should get negative 87 if you take this and dot it with any one of those three vectors.
Oh, so
Those
we
three.
take that in the dot product of anything. Okay.
Wait, the dot. Oh, so 87 is the dot product.
That.
Ah, shucks.
Yeah, fair.
With both the negative and positive versions, would that be correct?
Yeah, I think it's fine. I think there may be someone who demands like a standard form where the coefficient on x is positive or something. I don't know. I'm fine with either one. I would also probably have the instinct to divide through by 2 if all of them were divisible by 2. It's stuff like that, right? When you want, I don't know. I think we have a desire for beauty, and so those things are beautiful. I don't know. Here's an interesting question. How do you find the angle between two planes?
Sine theta equals.
Yeah, we do have an angle between formula, but what's the snag? That's the angle between formula for like two vectors. You could find a vector in the plane. That's a little tricky because there are many vectors that point in the two planes. You could find an angle between the normal vectors. We just have to. And let's draw a picture here. I think that's what this calls for. How's that for a picture? I don't know. We got two planes intersecting here. All right. So I guess the question in our minds is, would it work to consider the normal vectors somehow? Is there some relationship between the normal vectors to the planes, that angle, and the angle between the planes?
Because like that side and that side.
Maybe we need to simplify the diagram. Maybe we just need to go with it to here in this face down here. Just look straight down on it. This angle here is this. I mean, really, the angle we seek is maybe. I don't know. Can you convince yourself that that angle and that angle that I've marked very heavily there are the same angle? There are, which brings up a point, right? If you gave me either answer as a teacher, I could be like, yes, you're right, either one, right? So you could, yeah, at the end of one of these, you could give either this angle or its supplement, and I would accept either answer. Yeah, yeah. So can you tell that these two angles are supplementary? The sum of the angles here is 360. Okay, 180. Okay, so all right, are we convinced somehow here that all we have to do? This is the big aha. All we have to do is what we said earlier. We just have to convince ourselves with these pictures. Okay, well you really do just have to find the angle between the two normal vectors. Okay, but I had to draw a picture to like make sure that actually makes sense to me. So in the end, this will be easy. It's just we had to think about it. Find angle between normal vectors. So let's write what those are. I don't know what just happened there. So what are the normal vectors? I don't know. 2, 3, 1, right? Oh, -1. Okay, I'm trying to trick you up there, but what about over here? 5, -2, -1, right? Oh, 0? Oh, okay.
That one got me for a second. It really did.
I mean, there's only so much we can do to try to trick you up here, and you've seen it. You've seen all the tricks. Okay. Right now, just find the angle between these, right? Let's let temporarily, if you want to call that U and V, we're just finding inverse cosine of U dot V over magnitude U, magnitude V. And, you know, just tell us what you get. Call it a day. Put it in a box. 3 sig figs, you know?
Wait, so this is just like the other one? Yeah.
Give it a second. You know, everyone do that right now. I think you can do it before the class is up here. While I pass this out.
So how long did you do that?
Yeah, maybe Isa, you can show it.
Oh.
All right, Isai, you got it yet?
No, I can do the job part by myself. I'm good.
That's why the one you made in your list. You're finding an angle, that's being done fine.
Yeah, I know. Oh no, that's a crossing.
He's going to get any second.
Yep. Oh god, and so is the bell.
Penny beat the bell.
No.
You got this.
I heard I never find
What is it? 78 point something.
Degrees. I said the degree. I contribute.